Before taking our break, we were now to proceed to model-based reinforcement learning, and this is typically used when environments are well defined and unchanging, and where real-world environment testing is difficult. So the agent first builds an internal representation or model of the environment. It uses this process to build this model. It takes actions within the environment and notes the new state and reward value, then associates the action set transition with the reward value. So once the model is complete, the agent simulates action sequences based on the probability of optimal cumulative rewards. It then further assigns values to the action sequences themselves. The agent thus develops different strategies within the environment to achieve the desired end goal. In short, here the environment's dynamics have been inbuilt into the agent. For example, all those robots that work in a factory, they are built using the environment simulation, and the environment is taken good care of. So there is no changing environment here. And once this is done, the algorithm now just employs the state action pairs for optimal cumulative rewards. Then values are assigned to the action sequences themselves. Then the agent develops different strategies within the environment to achieve the desired end goal. So the different strategies we are talking about is basically the agent actually leverages different policies to achieve the desired end result. So the only difference with the model-free environment is that here the environment's representation has been actually built inside the model itself. So the model knows what the environment looks like and how to navigate it. But it is also allowed to take different strategies within the environment, which is it knows how it has been laid. Are we together? Hello? Okay. So some examples of model. Mhm. Uh, Pardon? Yeah, we are the one who is actually building the internal presentation, how it looks like. The game you are going to build, you are going to see. We are always building it and telling it how it looks like. You- yes. Examples of model-based reinforcement learning algorithms include DynaQ, Monte Carlo research, I think this is the one you're going to build, and model predictive control MPC. So how does DynaQ? Okay, so we not talk about DynaQ. Oh, iko hapo sasa. So the Monte Carlo research MTC MCTS. The Monte Carlo tree search is a decision-making algorithm that builds a search tree. Yeah, when you just hear the word research or tree, just know that it's a decision-making process using a tree. A decision-making algorithm that builds a search tree by simulating possible future actions and selecting the most promising ones based on the results of these simulations. It's commonly used in games and planning problems. Actually, the reason why it excels is the fact that you can simulate possible future actions. You can tend to predict future steps. You can tend to like try and think about future steps or future results. Then Monte Carlo research steps. Monte Carlo research involves the following key steps, which are done in iterations, which means done after that. One thing that stands out is what's called back propagation, which we are going to see how it works. But It involves the following steps, which is done in iteration. It's not done at like in a single step or in a single circumstance, but you're going to do it iteratively. Here, number one is the tree traversal. Tree traversal is basically to scan through the tree. Here, we calculate the value of upper confidence bound for trees, UCB1, given by the formula UCB as 1 is equal, it should be equals to VI divided by 2 into bracket the square root of that formula there, where SI is the state. So when we say SI, state 1 is the current state. State 2 is the next state, which is the next leaf of the tree. State 3, so basically we can have the stem, the branch, now the leaf is the last one. Now N is the cumulative number of actions for the initial state as 0. The initial state starts at as naught. That is when you've not done anything. You've not made your decision. And MI is the number of actions for a partition. So don't worry, you're going to work out using an example. But N is the cumulative number of actions. You count the total number of actions you've taken from the S naught all the way up to the current one S5. So that is the value of N. Then Si is the state. Then Vi is equals to 1 all over N for each state. So let's see how the formula. There's something that's going to happen at the following: node expansion, rollout or random simulation, back propagation, which I really need you to have on your fingertip because it's the one that's actually caused lots of problems when I explain. Then iteration, which is just repetition. Now, since I had not explained Q learning, let me just finish Monte Carlo, then go back to Q learning is when we can explain Dyna-Q. So Monte Carlo tree search diagram, algorithm for tree traversal and node expansion. This is from Massachusetts Institute of Technology YouTube channel. You can find it there. So we have the start. At the start, the current set is S naught. So you ask yourself, is the current set a leaf node? Meaning, are we done with making our decisions? The leaf node is where we make the decision. Is it a leaf node or a stem? If it's a stem, we continue. So if it is a stem, no. Then the current set is now a child node, meaning it now maximizes UCBI of SI, and probably it is now state 1. Then when you calculate the SI, you use the formula to calculate to update. Look at After updating, you ask yourself, you go back, is current state a leaf node? No, you do it until you reach the state when it's a leaf node. But when it is a leaf node, yes. Is the current Ni value for current state 0? Is the Ni value for the current state 0? Meaning we've not done anything. Yes, you roll out. If it is no, if it is not 0, you for each available action from current add a new state to the tree. Then the current is equal now to first child node. Then you roll out. Meaning we are always going back to the fact that it must be a leaf node is when you can roll out. So this is something that is now hard coded, and this is what is called Monte Carlo tree search diagram. It has excelled in games, especially the tic-tac-toe game, the online games, these big games that people play over the internet. The Monte Carlo tree search is the one that is used to develop. Now, how does it work? The rollout SI loop forever. If SI is a terminal state, return the value of SI. Then AI is a random or available action for the state SI. Now to simulate, now we simulate the AI with the SI, the action and the state. So with an example, is very much possible to understand. So Monte Carlo research in action. Step 1, random rollout value assignment. Look at this. The current state S naught, the T naught is equal to 0. the n naught is equal to 0. So when you go back, you might want to see what t naught is. Uh, so we said that Vi is equal to 1 over n, and n, where did Ni is the number of actions for a partition. So Ni is the number of actions. So how many actions have we done here so far? 0, meaning n0 is equal to 0. Then the t here is actually I don't know, it's not time. It stands for the number of it's number of something. Is it rewards? I think it's rewards, but let's see. I think it's the number of rewards. If I cannot, I think I've just forgotten. So we have action 1 and action 2. In action 1, for state 1, as the state 1, the t is still 0, the number of states have also been 0. Yeah, so we have a very good example in step 2. Now in step 2, we use the formula USBI SI to calculate the value. Aya, V was 20. What was V? VI is equals to T all over. I mean, this one cannot be expanded. Let me view from my T. If I could, in fact, if I can remember very well, T was the one that I used to explain easily. Here, USB1 SI is equals to VI plus 2 into ln of n all over ni, where SI is the state, VI is equals to T all over n for each state. T is the number of tree traversals, I guess. N is the cumulative number of actions, and so n. Okay, allow me just to ask AI to be sure. Otherwise, I'll end up. We said Gemini excels in things like that. So US upper class bound is the upper confidence bound for a given state as I. It is a value used to decide which child not to explore next during the tree traversal phase of MCTS. The node with the highest UCBY value is chosen. Okay. Then VI, this represents the value or average reward of state SI. The image clarifies that VI is equal to 0 for the state. This means the T is the total reward or total cumulated value obtained for all simulations that are passed through state SI. And then the number of times state SI has been visited. 2 is a constant. 11 n is the cumulative number of actions or total number of simulations play out from the initial state as 0. Then ln is the natural logarithm. Then ni is the number of actions or visits for a particular state as I. It represents how many times the state as I have been visited during simulations. So T is the total reward or accumulated score received across all simulations that are passed through or resulted from the state I. So T is the total reward for that specific particular state as I. If you download it, by the way, it won't be cut off. Everything will be given as it's in that case. Okay. So in step one, T is equal to 0 and naught is equal to 0. So meaning we take an action A1 and action A2. In set 1 now, resulting from action A1, T is 0, the total number of rewards, and the number of steps taken is 0. So meaning there is nothing. Then the same thing with the same part here, T is equal to 0, and the number of actions taken is still 0. Then we simulate it with V is equals to 20. Now, this V is always a random sana, the first one. So when we simulate it with V is equals to 20, T will be 20 and the number of actions taken is now 1. So which means that action 1 has yielded as 1, state 1, and action 2 remains the way it is. So when you back propagate, you go back to S naught. You see this N naught, it will actually keep on adding. When it adds to, when we do another state like action 3 now, yielding from S1. One thing that you should notice that when you perform two actions, a 1 and a 2, you choose the one that yields the highest value between the two. Probably now S1. From S1, it gives birth to action 3 and action 4. Then action 3 gives back to state 3. Action 4 gives back to state 4. Yeah. So when you do that, you use the UCB1 formula to calculate now the value that is going to be yielded. This one, because t is equals to 0 and n is equals to 0, UCB1 is infinity. Now, UCB1, between infinity and the value that's going to be gotten here, which one is the highest value? Infinity. So that's what has been chosen. So again, we've rolled out with a random value of 10, V is equal to 10. Then we back propagate. The number of actions that have been taken now in 2, because n now increases to 2. Then the total cumulative reward becomes 30. Again, you calculate using the formula. The formula guides us. When you calculate using the formula, this other one was 21.67. This other one is now 11.67. So which one is higher between the two? 21. So you roll out from this one. So when you do this, you assign again another value of V, like it's always random. So when you assign again, it's just back propagating. The number of actions that have now been taken is 0 and is equals to 1. When you back propagate to the initial state as not, the cumulative totals are now 30 because 0 plus the previous 30, whereas the number of actions taken are now 3. Action is just basically calculated with what has been done with the UCB, not what has been done with, because you will say that it's a 4, action 4. No, action is taken with what you have done after calculating the upper confidence bound. So again, you calculate the confidence bound for this one. The confidence about for this and for this. Here, the one that will yield the best should be S4 because it will definitely have the infinite. I'm going to find you this YouTube link. This professor knows how to explain it well. So I don't know why here issue it is not again F4. So, okay. So but I'm also going to do research on this. So when the day after tomorrow when we're building this model, we will actually look in depthly into the this again, the theory part of it before we build it. Remember, this thing will not stop. It is iterative. It will go on. So the more leaves you add on to this entire process, the better your model becomes. Yeah, it goes back propagates. I'm not understanding why this one is not. They are not considered as four. Don't understand why. This one should be five. I think it's just typing error. Should be five if I'm not. um, In fact, six. Mm. I'll visit the example again and watch and see what is done there. For Q learning, which are not going to build anyway, because you cannot tell me I should build a self-driving car, to be honest. But to train you on, by the way, inaitwangaje Amazon's depress depressor. So kindly visit this link. Just search for Amazon depressor. Come here and read more about this. It's one of the best examples of it's one of the best examples of learning or model free algorithm. Once start building it, so actually the best thing with them is that they will teach you how to go about it step by step and what it is. So this is the environment, simulation environment, and the policies and everything. The obstacle is there, so everything, and it's a competition that is. So as you can see, they want me to log in, and I'm not ready for that. Okay, so you will visit Amazon Depressor and see how it works. So how Q learning works. Consider the following example of a frozen lake. The agent must cross the frozen lake from the start to the goal without falling into the holes. So the goal is to use the shortest route possible. So the agent must use route R2 or route R1. But at the end of the day, it should be the shortest route possible. So how many steps are you going to count from here and how many steps are you going to count from here? So if one, two, three, four, five, and again one, two, three, four, and five. So for in this case, the steps are actually identical in number. So there is no problem. But at the end of the day, it should just avoid falling into these pitfalls. So if the agent goes straight from here to here, it falls into the frozen. If it goes diagonally, frozen lake. It goes to the end, frozen lake. So Q table, the agent will use a Q table to take the best possible action based on the expected reward for each state in the environment. In simple words, a Q table is a data structure of sets of actions and states, and we use the Q learning algorithm to update the values in the table. In simple words, a Q table is basically a list which has both the pairs, not a list, key value pair. That is probably a dictionary. So probably a dictionary that has the key value pair of state and action. So we've just drawn it to actually signify to actually simulate states. But it is a data structure that, like a dictionary, that has the key value pairs, the state and the action taken. So the Q function and the Bellman equation. For you to update it, it uses a function called the Bellman equation. I'm going to go through this very fast just to give you a theoretical sense of it because we're not building it, but it is what is actually being used by the Amazon guys, the praiser here. Yeah. So look at the Q value of state st, the Q values for the state given a particular state. Then we have the expected discounted cumulative return given the state and action. So the expected return RT1 plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3 all the way up to nini. So this is a polynomial function given the state at st and at. So the values of gamma y's, gamma and gamma squares are actually, how can I call them, are just coefficients of the rewards. So I really encourage my students to go over bit. But this, this is masters, to be honest, masters and above, because we were not even taught all these during the bachelor's degree, but they are just notes I pulled over when doing research on more research on this. So the Q learning algorithm process, you initialize a Q table, which is not a table in the sense, but it is basically a key value pair dictionary with state and action. So you initialize that data structure, then choose an action. Perform the action, measure the reward, update the Q table, and go back, choose an action again, perform the even until you reach the best desired result. So we will build the table with columns based on the number of actions and rows based on the number of states. In our example, the character can move up, down, left, and right. We have 4 possible actions and state rewards: start, idle, wrong path, and end. You can also consider the wrong path for falling into the hole. So we initialize the table with values as 0. So in Amanisha, the current set is as 0, action is a 0, so value is 0. So the start, go back, move up, move down. The start, the idle, the hold, the end, everything is at 0. Choose an action. At the start, the agent will choose to take the random action. For example, in our case here, I'll use the one on the web to it is going. In our case, it can go down or go right. In left and right. Okay, so down or right. On the second run, it will use an updated Q table to select the action. So perform an action. After selecting the action, if it can either go right or down. Choosing an action and performing an action will be repeated multiple times until the training loop stops. If the actions, if the first action and set are selected using the Q table, in our case, all values of the Q table are initially 0. Then the agent will move down and update the Q table using the Bellman equation that we looked at here. So it will use this Bellman equation to update it. Yeah. So, which is basically a formula that has a lot of calculations thereafter. Then after that, with every move, we will be updating values in the Q table and also using it to determine the best course of action. Initially, the agent is in the exploration mode and chooses a random action to explore the environment. The epsilon greedy strategy is a simple method to balance exploration and exploitation. You see the exploration and exploitation trade-off, the one we were talking about. So there is an certain strategy used to balance. It's called the epsilon greedy, which I urge you to go and do more research on. Then, by the way, the purpose of this course is just to give you a tip of what is always in the reinforcement learning, so that if it interests you, you go ahead and do much of the research. Then the epsilon stands for the probability, and that's why I have not even rolled the AI engineering course, because I know I cannot teach what I'm not good at yet. And the epsilon rate is higher, meaning the agent is in the exploration mode. While exploring the environment, the epsilon decreases, and that's now the epsilon grid strategy. Uh, the epsilon decreases, and agent starts to explore the environment. During the exploration, with every iteration, the agent becomes more confident in estimating Q value. So when it moves down, we update 1. So after measuring the reward, after taking the action, we will measure the outcome and the reward. The reward for reaching the goal is +1. The reward for taking the wrong path or falling into the hole is 0. The reward for idle or moving onto the frozen lake is also 0. So after moving right, what else? If you go back to the one on the web, it moves right. If it goes down, it will be 0. So it must just move right again. Move right again. So if we move right, we'll update 2 +1. Then we move down +1 +1. If it goes down 0 +1. So that way until you are done. So, and this is update the Q table. We'll update the function QSTAT using the equation. It uses the previous episode estimated value, Q values, learning rate, and temporal differences error. So the process is repeated multiple times until the table is fully updated. And when the table is now fully updated, uh, basically it's now sentenced to how you're going to update the table. That if it moves right, it moves down 1, moves down +1, that is 2. It moves right +1, moves right +1, then moves down +1, then to the corner +1. But if it moves right +1, because it is not falling into a hole. If it moves down 0, we are done. It starts again. That's episode 1 is done. Yes, and then we also start again, move until we now reach the end results. That's how Q learning works. Now we can bring in a neural network strategy, which we are going to look at in the next few weeks after the after our nini after things are now becoming wonderful. Then after doing that, we shall just revisit briefly how we can incorporate neural networks into this to form deep Q networks, which is now the next one here. But tomorrow, kesho kutwa, we shall look at Monte Carlo search. Now I have 2 things to do research on, the PCA, and then tomorrow, then build Monte Carlo the other day. After building Monte Carlo, that will mark the end of reinforcement learning. The reinforcement, the Monte Carlo you're going to build is actually a game, tic-tac-toe game, and you'll see how it plays with us very well and very, very perfectly. Now, DynaQ is a reinforcement learning algorithm that combines model-based and model-free approaches. That's why it's called DynaQ, dynamic. It learns a model of the environment's dynamic and uses this model to simulate experiences and update Q values, combining the advantages of both model-based and model-free. It is used mainly in robotics and simulated environments such as testing self-driving cars. So DynaQ is the one that is used for self-driving cars because both we've simulated the environment and at the same time we are working in the complex environment. And that's why it can be contrasted with Q-learning. It aims at combining model-based planning with free model learning such as Q-learning. And we say that Q-learning is a RL algorithm used to find the optimal action selection policy for a given MDCP, as we've seen. Moving right one, moving right again one, moving down one, evo evo. We further notice that it learns an action value function QSA, which represents the expected cumulative reward for taking an action instead, which we've done with the table. With DynaQ in the model now, the agent learns a model of the environment from its experiences. So with DynaQ, there is also the model of the environment taken into consideration. Then the model captures the probabilities of transitioning from one set to another using the Bellman equation. So, mhm, mhm. we are sim- we are simulating. Did you hear me talking about a big company acquiring a land somewhere and just simulating the Nairobi city how it should look like? That is the inner queue now. That is the inner queue in action. Yeah, yeah, something like that. Which takes a lot of years. Actually, Waymo was built in more than 10 years. So something like that for you to release it into the market, it must be perfect. So we are waiting for a self-driving double-decker bus, which will change the public transport forever. Drivers will make a lot of noise, matatu owners and everybody. Yeah. But you guys who are going to build it and analyze data, will just be in oil because we will advise the drivers to enroll for machine learning classes. Yeah, so I hope you have answered how DynaQ works. When we take an action A in set S, we end up in the next set S. Then R is the reward for taking this action. We iterate this process when we apply the Q table using the Bellman equation. Remember Q learning. The key term here is we're just using Q learning, except that in a simulated environment or in an environment whose model has already been pre-built. Yeah, so when selecting actions, the InAQ typically uses an epsilon greedy policy. And what did you say about epsilon greedy policy? We said that in this greedy policy, we are always this one is getting lost. Tunamalizanga the current episode until we get the results. Then if we fail, we start off again. What we are doing with Q learning. When we move into the frozen lake, we started off again. Yeah, so that one we say that the first episode is done. The first epsilon, not episode or epsilon. Did we say epsilon or epsilon? I don't want to use a word that is not. So with probability E, the agent selects a random action to explore, and with probability 1 minus E, it is select the action with the highest expected reward according to its land Q values. Okay. So with probability E, the agent selects a random action to explore. You know very well that probability add up to 1, meaning the remaining probability is 1 minus E. So with this 1 minus E, so if it has explored, then 1 minus E is the remaining probability. This is now where it selects the action with the highest expected reward. So it uses 1 minus E, the remaining probability, to perform an action. If it uses this one to explore, then the remaining one is to perform an action. To update it is just using the Bellman equation. Like, remember, this is just Q learning, except that the environment model has been simulated. Then application of reinforcement learning. Hata before Wambiwe, you just know that this one is used in game playing, robotics, autonomous vehicles, and with a lot of caution recommendation engines, which I think is benefits, excels in complex environment, requires less human interaction, especially after release to the market, optimizes for long-term goals. Yeah, we are not interested in what is near us, but what is it going to give us. Challenges associated with reinforcement learning, practicality, I mean, Germany, sample inefficiency. Market share cannot build. Yeah, then exploration and exploitation trade-off. You see, we do not know the epsilon and 1 minus epsilon. They want to use to explore and they want to use to exploit. It is very difficult to know which is the best, because sometimes what if the one used to exploit is higher than the one used to exploit? Problem with reward engineering. How are you going to reward the agent? In most cases, it's always data scientists defined value. Human beings are prone to error. Germany, number 4, some cases might be difficult to interpret. You see Monte Carlo search. I've really found out. The good thing is that God told me, my son, if you don't know how to explain, don't force yourself. Go do research first. You might want to ask which God, where did you meet him? Then the safety and ethical considerations. This is self-explanatory. Is it going to cause accidents? The self-driving car. So, is it going to break down? What is the high probability that it's going to cause 1, 2, 3 with the government? So these are something of the things that reinforcement learning comes with. And with that marks the end of reinforcement learning. So we have two models to build. PCA with, I think we'll combine with logistic. Then move on and build. If we combine it with logistic, we will go back and revisit our model we built with logistic and see the results we got when we built that model with logistic alone. Then compare when we did PCA and built logistic and make our new. That's how powerful data science is. Then we shall now take a break after building that this week. But before break, we need to deploy one model. I think here PCN and logistic can work well in our case. So it's the one we might want to deploy on Google Cloud Platform. Otherwise, you might be asking yourself, why did you give us an email account? It was for accessing our Google Cloud Platform, which we're just going to deploy. Once you may deploy Vizuri to simulate in production environment to Natoa, then I tell you, we will now use your 300 credit from Google. Google gives 300 credits free for newcomers. I guess for 3 months, you will use that for your own building models. I didn't want to introduce you back then because I knew while learning it is always very difficult to also leverage it. Itaisha before unini. So once we are done, tutakuja tu kwa deep learning, which is always very short but detailed. Hata sikumaliza kutype notes.